So direct current, we have the electrons flow. And in any electrochemical cell, be it voltaic or galvanic or electrolytic, which direction do electrons flow? Electrons flow from anode to cathode. Good. How do you know that? Because that's the direction they go. They go in alphabetical order. Okay, it's because the anode is where oxidation takes place and it's losing electrons. The cathode is where reduction takes place, it's gaining electrons. All right, this is all beside the point. We need to have that DC power supply. And in our beaker, we are told that we have nickel sulfate, so we have nickel 2+, and we have sulfate SO4 2-. And because it says 1 molar, and also in this case it's really generous to you and it says aqueous, you know there's another substance in there as well. It's not just molten NiSO4, you also have water, yes? So when you are looking at your substances, nickel, sulfate, and water, we need to find the one that requires the smallest voltage in order to run. Because when you start turning up that DC voltage, you're going to have the option. Am I going to reduce my nickel? Am I going to reduce my sulfate? Am I going to reduce my water? Which of those is most favorable? Yes? Am I going to oxidize my water? What else could I possibly oxidize? So we're going to list possible oxidations, and we're going to list possible reductions. So what are the things that could get oxidized? Is it possible for nickel 2+ to be oxidized? That would mean that the charge of nickel was getting bigger. Have we ever heard of nickel 3+ or nickel 4+? No. So nickel cannot be oxidized. It can only be reduced. So we will put it in our list of possible reductions. How about sulfate? Well, sulfate I probably would want to look on my table because it's a bit more complicated. Yes, so let's check our data booklet and let's look for sulfate. So sulfate can get, if it's over on that right-hand side, it can get what? Oxidized or reduced? Oxidized. So SO4 is possible to get oxidized. So I will write it in my possible oxidations. Let's see if it's possible for it to get reduced. Let's see, we had the SO4 2- here. We have SO4, I feel like it's somewhere else. Or maybe I'm wrong. Oh, here it is. However, this SO4 is not the only reactant there. What is the other reactant? Hydrogen. Do we have hydrogen, H+, in our beaker to any significant amount? Let's go look. We have nickel, we have sulfate, and we have water. Where is my acid? Is there acid? No. If there is no acid, you cannot use this one. This one requires acid. You will actually see some of these reactions that say, for example, this one says H+ 10⁻⁷ molar. Now, we haven't talked about this yet because we haven't done acids and bases, but 10 to the negative 7 molar is the hydrogen ion concentration in neutral water. Okay, so if it says that, that can happen in neutral water, but anytime you see a hydrogen like this, that means you need to have some acid present in order for that reaction to occur. Is good? Okay. Excellent. Now, where did I get to? We were here. Okay. So SO4 can get oxidized, but SO4 2- needs H+ to be reduced. And so that one is a no. Okay. And water. Water is always capable of being oxidized. It's always capable of being reduced. Did you guys get that from the videos? Yeah? Okay, so water is always an option. And since our electrodes are inert, we don't have to worry about them undergoing oxidation. Yes? Sometimes you'll have a metal electrode that could undergo oxidation, and that's a possibility, but not here. Here our electrodes are inert. So we really only have two choices for each of them: sulfate and water, and nickel and water. So let's go look those up. So for the two things that could be oxidized, I have sulfate, which could be oxidized, or I have water, which could be oxidized. Remember that when we're going backwards, what's the voltage for the oxidation of sulfate? So if I'm going backwards, it would be negative 2.01 volts, yes? Is that a favorable type reaction? No. Let's look at our water, okay? So when water is oxidized, its oxidation potential is negative 0.82 volts. Still not favorable, but is it better than sulfate? Yes. So if you look here on the side, we have, this is our strength of reducing agent. I think there we go. Yeah, strength of reducing agent. And if you're a reducing agent, you are getting oxidized. So the strength of the reducing agent is how good are you at getting oxidized? So who is better at being oxidized? Sulfate or water? Tell your partner, who's better at getting oxidized, sulfate or water? All right, tell me, sulfate or water? Water, yes. Because water has a less negative voltage, it'll be easier to get it to get, it's less non-spontaneous, okay? Our other choices were for our things that get reduced, also water. And one thing you'll notice about water is that they are in the little gray lines, okay? Get rid of these ones because they're just confusing. Here is water. And if you are confused and you're like, hang on a second, there's another water down here, This would be water in basic solution. Okay, so don't worry about that unless we are in a base. Do we have a base? Let's go back. Take a look. No, we got sulfate. Sulfate is minorly basic, but not very. It's a very, very weak base, so I wouldn't even worry about it. Right? Who said that? Where are we? Yes. Is there any hydroxide here? No. So then you don't worry about that one. You just say, okay, we're going to go with this one here because, again, it's got that 10 to the negative 7 molar. That's neutral water. So that's the one we're going to choose. Yeah? Yeah. So we got the water there, and nickel is, where's nickel? Oh, it's got to be up. Nickel. Oh, it's up. There's nickel. So these are being reduced. So this is my reduction potential, and this is my reduction potential. Who is less bad at getting reduced? I know that sounds terrible, but neither of them are like particularly good because they're negative values, yes? Who is better at getting reduced? Nickel is better at getting reduced. It's got a higher reduction potential, yes? Now, another way to look at this, if you have your chart in front of you, and this is going to require me to zoom out a little bit, and I'm going to get rid of that one because we don't want the one that requires acid, is, okay, there we go. Oh, come on, behave. There we are. Okay. This is easier if you've got like a bigger thing, but it's tiny. It's okay. Do you remember the uphill and the downhill? Spontaneous, non-spontaneous. So you have a choice as to which line, which hill you're going to climb. Do you want to climb a hill from water up to sulfate? Or would you prefer to climb a hill from nickel up to sulfate? Or would you prefer to climb from nickel up to water? Which one is easier? Nickel to water, that is the easiest hill to climb. And so those are the reactions that are going to be preferred. You can also look at it from the sense that this has, the water has the more positive, less negative oxidation potential, and the nickel has the higher reduction potential. So you're looking for the higher of the two voltages in either case. So what is the voltage of the cell going to be? It's going to be the difference between here and here, yes? So we're starting at negative 0.26 and we're finishing at positive 0.82, yes? And so that difference there is going to be the voltage. You can formalize that by using your E0 cell formula. Yes? But sometimes it's nice to just look at the picture and say, oh, my voltage is just the difference between these two. I need to pump the electrons up that high. It's kind of a nice visual. If you don't like it though, just go with so we decided that it was water is better. And in this one, it was nickel, which is better. So our oxidation will be H2O. And then I would have to go back to my data booklet. Oxidation of water is half O2 plus 2H plus. Okay, just copying it right off of that. Oopsie, come back. There we go. goes to 1/2 O2 plus 2H plus 2 electrons. And our reduction potential for that is, or sorry, oxidation potential for that was negative 0.82 volts. Nickel getting reduced, I don't even need to look that one up because that's easy enough. Ni2 plus is going to gain some electrons. It'll gain 2 electrons and become nickel solid. And the E naught of reduction is, where's my nickel? Nickel. There you are, negative 0.26. And so the E naught of the cell then is going to be the reduction potential plus the oxidation potential. Do you guys prefer the other formula or is this one okay? This one's okay? Anyone care? Would anyone like to see it the other way? Nobody? You want to see it the other way? Okay. So for this one, the E naught reduction, actually here, I'm going to do this and then I'll do that because otherwise I get too confused in my head. So we have the reduction potential, negative 0.26 volts, plus negative 0.82 volts, and we get whatever that is. That's what, 1.08? Negative 1.08 volts. Did I do my math good? Well, okay, so that is the voltage of the cell. Is this cell going to run on its own? No, it is non-spontaneous. So if I have my power supply and I turn my power supply up to 0.5 volts, will this cell run? No. If I turn it up to 1 volt, will this cell run? No. If I turn it up to 1.1 volts, will this cell run? Yes. So basically when they're asking you what voltage does it need in order to proceed, the required voltage to run the cell is positive 1.08 volts. And I often like just to put a little greater than in there just because, sometimes it just needs that little kick past 0 volts to get going. Yes? All right, so that was so far so good. We were asked to find the products produced at each of the electrodes. So if this is oxidation, I will come back to your thing in a minute. The possible oxidations, what's going to be produced at the anode? Well, that's going to be, come on, here we go, oxygen and hydrogen are produced at the anode. Yes? Mm. Mm-hmm. Yep. And then over here, what is produced at the cathode, because that's where reduction takes place, that is going to just be nickel solid. So that's what they're looking for there. If we were to do this as a E0 cell equals E0 of reduction at the cathode minus E0 of reduction at the anode. This one remains the same, yes, so that's going to be our negative 0.26 volts. However, for the anode, what we need to look at is not what's actually happening at the anode, but what would the reduction reaction be. So that would be the reverse of this, so it would be 1/2 O2 plus 2H plus 2 electrons gives us H2O, and the E0 of reduction for that is positive 0.82, right? 82. Yeah, and so then we would go minus positive 0.82 volts, and you end up with the same negative 1.08 volts. Yes. Some people like it. I don't know. Personally, I find this less intuitive, but if you're simply looking on here and you're kind of doing it like this, you know, where you've just got you're looking at the difference between them, you would take 0.82 and you would subtract negative 0.86, I don't know what I'm saying. Anyway, it works either way. Yeah, that just did not go well. I need to have some lunch is basically what I need to do. Brain is a little bit, yeah. How are we doing with electrolytic cells in general? In general, we're good? So, would you be willing to watch the rest of the videos this weekend? Pardon me? On the ones on the list? Yes? And then you could try number 3. So watch the rest of the videos and do number 3. Yeah, there's a whole bunch of parts to it. It's like A, B, C, D, blah, blah, blah. Yeah? Would you like to go over another example or would you like to have your lunch? I'm good either way. Electroplating, yes, we could. Yes. Electroplating is a special example. I keep clicking on the wrong thing here. And if you're having difficulty with electroplating, the Tyler video on electroplating, you know, he does his usual thing where he's got atoms going wherever they go, so that's going to be probably helpful. Electroplating is, in essence, what you need is you need a beaker and you need something you want to electroplate. So let's say that we have, I don't know, a nickel. Okay, and we would like to electroplate it with gold. Yes, I want a gold-plated nickel. So, if I want to get gold to go onto the nickel, what do I have to have in my solution? Oh, is that not early? Oh, I guess not. I can go over this next week. Does that sound good? Yeah. So watch the rest of the videos and do number 3 on that worksheet. Hi. Uh-huh. Oh yeah.
When the electrons went into I think the other metal, I think
Yeah.
the nickel.
Uh-huh. Yep.
So why wouldn't the nickel just become ions, negative ions? Why does it?
Because it can't. Nickel doesn't do that. Metals do not become negative ions. They can't.
Oh, really?
Yeah.
Oh, okay.
Yeah. Because they've got gaps in their valence. They don't have gaps in their valence shell. They want to lose electrons from their valence shell.
Okay.
Yeah. Yeah. Hi. Yes, I did. Most of it. I missed the first little bit, but I did. Huh? I will be posting it. Yes, I will. It's just in one direction you are writing the reduction potential, and in one you're writing the oxidation potential. And the oxidation potential is always the opposite sign of the reduction potential. Yeah, so you'll subtract if you're doing reduction, and you'll add if you're doing reduction and oxidation because you're already changing that sign, so that's like subtracting. Yeah? Yeah. Okay, cool.